Okay, so this is my video explainer 4, where I do problem 12.28 from homework 2. The problem has the situation where there's a 4 kilogram, 36 centimeter diameter metal disc, which is initially at rest and can rotate on an axle along its axis. A steady 6 Newton tangential force is applied to the edge of the disc tangentially. Note that that's pretty important. It's generating torque, and if it's perfectly tangential, then it all goes into the proper component of torque. What is the disk's angular velocity in rotations per minute 4 seconds later? And that is an important problem. So, and express it in RPMs, revolutions per minute. And so our strategy really is to draw a picture. We've written all of our known quantities. And this picture I drew, you can see there's the applied force, which is, the 6 newtons. The mass is just kind of all over this disk, of course. And then we have the radius as well. And then this little dashed line is the axle, I suppose. And so this problem is going to involve torque. We know that because of the force. And so torque equals the moment of inertia times the angular acceleration. And since we're trying to look for angular velocity, and we know what acceleration is equal to the change in velocity over the change in time, angular velocity is much the same. It's the change in rotational velocity or angular velocity, over the change in time. And this is really important and helpful, especially because we know that the disk is at rest initially, and so the change in omega, or in our rotational velocity, is going to be the final rotational um, velocity after those 4 seconds. Um, so yes, here we go. And so we're solving for acceleration. So let's plug things in here. So torque equals moment of inertia times delta omega over delta t. Sorry, my omegas are not great. Okay. And so we know delta W torque equals. So then we end up having this. We have torque times delta T equals I omega. We're solving for omega, so then we get omega equals torque delta T over moment of inertia. All right, and so over here, if we look to the left, we have moment of inertia. We know it's this integral, and you would basically solve over the kind of area of the disk. I guess you would use dm, which is like the mass of the disk. But anyways, we generally know that it's 1/2 mr squared. And I could do the math, but that would take a lot of time. But it's 1/2 mr squared, which is important. It's different for most objects, but for a disk and also for a cylinder, I think, a uniform cylinder, it's 1/2 mr squared. And so that's an easy one to remember. So now, if we plug in, and also we know that torque is equal to force times radius, because it's essentially the angular component to force. Well, angular analogous quantity to force. So Fr delta T over 1/2 mr squared. Oh boy, look at that. The r's cancel, and so we get omega equals force delta T over 1/2 mr, which is, once again, the same as force delta T, 2 force delta T over mr. And so now we just have to plug things in. And what we get is 6 newtons times 4 seconds over, 2 times that, over 4 kilograms times 0.18 meters. And what we end up getting is omega equals 67 radians per second. Of course, they want it in RPMs, and so we have to multiply. And so 60 seconds equals 1 minute. And then multiply again by 2 pi radians equals 1 rev. And the answer we get is 640 RPMs. And that is our final answer. And it's pretty high, but still pretty reasonable. And the units all check out. Well, more or less. They all kind of cancel out because newtons, components of newtons cancel out with kilograms and meters. And so then we're left with seconds, which works. Really, the most important thing is to draw this picture. Recognize, if you have all these quantities, you can solve the problem pretty easily. You just have to remember that you can solve without doing this, but it's helpful to know that because it starts at rest, the change is the final, because there's zero initial. So WF, omega F minus omega initial equals omega F. So yeah, that's my suggestion. Torque equals force times radius, and that's pretty